Thanks to the Event Horizon Telescope, we're learning a tremendous amount about the supermassive black hole at the heart of the Milky Way and the one at the heart of M87. And just to know that we're seeing effectively the event horizon around a black hole is kind of mind-boggling. And it took a telescope the size of planet Earth to do this. But there are many other thorny problems about black holes. And one big outstanding question is, how fast is the black hole at the center of the Milky Way spinning? And how do astronomers know? How do you figure this out? Well, my guest today is Dr. Ruth Daly. She is a professor at Penn State, and she has developed a technique for measuring the spin rate of supermassive black holes and has used that to calculate the spin rate of the supermassive black hole at the heart of the Milky Way. Now, I'll warn you, it's a very technical conversation, and Dr. Daly doesn't filter the complexity of her language, maybe because I asked her not to. So, she's going to throw out a lot of terms which are very advanced, but hopefully if you stick through, some of it will all start to make sense as we sort of tell this larger story. All right, enjoy this interview. I've heard that there's only a couple of things that we can actually know about black holes. What can we know?
Well, there are three characteristics that we can study regarding black holes. One is the total black hole mass. The second is the spin angular momentum of the black hole. And the third is whether the black hole has any charge, electric charge. And for astrophysical black holes, they can have a charge, but it's small and it generally will not be an important component. So for astrophysical black holes, like real black holes in the universe that we study, which could be stellar mass black holes or supermassive black holes, we're interested in the total black hole mass and the rate at which it's spinning, the spin angular momentum. However, those two quantities lead to three important quantities. There is the total black hole mass, which is what we measure in astronomy. If we go out and measure the mass of a black hole, we measure what's called the total dynamical black hole mass. There are two contributions to that. There's the rotational mass energy of the black hole, which depends on how rapidly it's rotating. And there's the irreducible black hole mass, which is something that might be considered like the rest mass that fell into the black hole. But it's the black hole mass that there are no processes other than Hawking radiation that can ever decrease the irreducible black hole mass. But there's a third very important quantity called the spin mass energy, which is available to be extracted. And that is different from the rotational mass. So not all of the rotational mass energy of a spinning black hole can be removed from the black hole. Only part of it, which we call the spin mass energy, can be removed. And in the types of studies I'm involved with, where we're looking at jetted outflows from black holes, both stellar mass and supermassive black holes, it's that spin mass energy available to be extracted that's very important, and that when it's extracted can really modify the local and large distance regions around the black hole.
Wow. So, when we think about, say, your classic Newtonian method of measuring the mass of an object, if you have like a planet and a moon, you can measure the mass of the planet by the orbital characteristics of the moon. But what you're saying is that you have imagine a spherical cow, imagine a black hole that is not rotating. There is the mass, all the stuff that went into the thing, but just through its pure rotation, the mass calculation of that black hole gets more complicated.
That's correct. So it's really fascinating. So there's when you study the total dynamical mass, yes, if that black hole is spinning, then it has a rotational mass energy component. In other words, the energy of the rotation adds to the total black hole mass. And it actually adds in what we call quadrature. So the total black hole mass squared equals the rotational mass energy squared plus the irreducible mass squared. So they don't add linearly. But what does add linearly is the spin mass energy that could be extracted theoretically, plus the irreducible mass equals the total black hole mass. So what that means is that it's possible that there are processes to extract the spin energy of a black hole that will actually decrease the total dynamical black hole mass. Now, I'm not saying that's what's happened, that is what is happening, but it's theoretically possible.
Is that the Penrose process that you can extract, in theory, you can extract mass from this black hole combination and then use that as energy?
That is exactly right. That is the Penrose process. Mm-hmm.
So when I think about even when people ask me this question, I'm explaining it to them, like when we see these jets coming from quasars, and this, I always sort of explain to you, like, black holes absorb all that falls into them. How can they produce these jets? And I'm saying it's not coming from the black hole. It's coming from the region around the black hole. It's coming from the accretion disk. But is that connected to this rotational mass energy that you're talking about?
Absolutely. There are many different models for how jets and jetted outflows are produced by what I call a black hole system. And the black hole system is the black hole, either rotating or non-rotating, and the accretion disk around it. And then I also include the jetted outflow. It is possible that there are several different mechanisms that lead to powerful jets. The method that I have developed and used along with my collaborators to study how rapidly Sagittarius A star is spinning is a model where the jetted outflow, or a jetted outflow, and we think that the radio blobs, moving away from Sagittarius A star are the basis of a jet, of a weak jet, but it's a jet. That is being powered by black hole spin energy extraction, or a combination of a wind from the disk plus the black hole spin extraction. So the sources that I have been studying have unusual properties when we look at the strength of the outflow relative to the strength of the emission coming from the accretion disk and the total black hole mass. So for these systems, and Sagittarius A star happens to be one of them, M87 is also in the sample, they have a special set of properties, which the way these properties all align fits in extremely well with what we expect for a spin-powered jetted outflow. So, but there are other processes, but there are many, many models for spin-powered jetted outflows, and especially for sources where the power in the jet is large compared to how bright the accretion disk is.
So if we could fly to Sagittarius A star and see this, be in the vicinity of it and see what's going on, it's not a full-on quasar, but what would we see in its environment if we could get close enough to the black hole and get a sense of that jet system that's going on?
Right. Yeah. So Sagittarius A star right now it's a very, very weak source in terms of everything about it. It's a relatively low mass supermassive black hole. It's only 4 million times the mass of the sun, as opposed to M87, which is 6 billion. Sort of like imagine your salary increasing by a factor of 1,000. That's the difference in these black hole masses, over a factor of 1,000. So it's a relatively small black hole. It has a very weak accretion disk. So the luminosity is around, I think it's around 10 to the minus 6 of the maximum possible luminosity, the Eddington luminosity. I'd have to look at those numbers again. But it's relatively weak disk, and the radio emission that's coming out is relatively weak. But the proportion of the radio emission to the X-ray emission in the context of the mass of the black hole fits in extremely well with the spin-powered outflow model.
Right. And so your team, I guess, what tool did you use to make your observations of the outflows?
Right. So I have developed a method which I call the outflow method to use the properties of the outflow in conjunction with the total dynamical mass of the black hole and the properties of the accretion disk, the brightness of the accretion disk, and the X-ray is a nice wavelength range to use for that, and have written those equations in a form where I can line it up and identify terms with a general theoretical expression for a spin-powered outflow. So if you write the general theoretical equation I write for that would sort of be representative of a spin-powered outflow does not assume any particular spin-powered outflow model. It's just these are all the ingredients, and we write it as a functional form, and then we have a bunch of exponents that get solved for using data. And then we line up all the data with that, and that allows us to solve for the black hole spin. I believe the outflow method is the only method that anyone is using where the properties of the outflow are an ingredient to determining how fast the black hole is spinning. So other people have looked just at the properties of the accretion disk or many pieces of information regarding what's happening in the immediate vicinity of the black hole. So this work is different in that it includes the properties of the outflow as one of the key ways to determine how rapidly the black hole is spinning.
And I guess what observatory were you using to be able to observe the outflows coming from Sag A star?
Right. So part of the collaboration included Daryl Haggard and Anand Liu from McGill University, and they had published a study where they had simultaneous Chandra X-ray observations and VLA radio observations of Sagittarius A star. They found that that basically the X-ray was sort of bubbling along and the radio was sort of bubbling along, but they're not coming from the same region. They weren't varying exactly in sync. They were sort of each, going up and down, up and down. And also during one of their observations, there was a bright X-ray flare, which means that the brightness in the X-ray increased by about a factor of 10. Now, the radio emission did not have a similar increase. And so the outflow method, what we did was we reanalyzed, Megan Donahue, who's also on the team, reanalyzed all of the Chandra data and what solved for what's called the column density. So one thing that happens with Sagittarius A star is we're looking right through the plane of our galaxy. So there's a lot of stuff between us and the black hole we're trying to study. And one of those is the amount of neutral hydrogen. That's called the column density of neutral hydrogen. And that turns out to be a very large number for Sagittarius A star because we're looking right through the plane of our disk. So to get that number, Megan looked at all 6 X-ray data sets together because that number is going to be the same. It's not going to be changing, from day to day. So she reanalyzed the data, all that Chandra data, and then we use the simultaneously obtained radio and X-ray data to apply the outflow method, knowing that the radio emission is not coming from the same region that the X-ray emission is coming from, because they don't vary in sync, which is what we expect in the outflow method. The X-ray emission is associated with a corona or accretion disk quite close to the black hole, and the radio emission is associated with an outflow, a weak but yet an outflow of material that is being released from the polar regions of Sagittarius A star. So we combined that simultaneously obtained data to solve for the black hole spin. And amazingly, even the data which was 10 times brighter in the X-ray still gave a black hole spin parameter, spin function, and dimensionless spin angular momentum that was consistent with the other three values within the uncertainties.
So what were the results? How fast is it spinning?
Okay, so another thing that I try to stress is the parameter that most groups discussed is called the dimensionless spin angular momentum parameter. So it's the dimensionless angular momentum with which the black hole is spinning. However, there's another thing called the spin function, which I like to work with, because the spin function, there are several reasons you want to work with that. First of all, the spin angular momentum varies between 0 and 1, the dimensionless one. Of something that's spinning with a spin of 1 is maximally spinning and has the maximum spin energy that you could extract. If you go only to 0.9, which is what we found for Sagittarius A star, you're down to 1/2 of the spin energy available. In other words, the available spin energy is now half of what it could have been if it was maximally spinning. So we call that a very nonlinear relationship. However, the spin function has a very nice linear relationship with a lot of quantities. So I prefer to work with that. So getting a dimensionless spin angular momentum of 0.9, we were able to obtain the spin mass energy available to be extracted, and it was only about half of the maximum. And we actually got a number for the spin mass energy that could be extracted, and it was only 6 times 10 to the 5 solar masses. So since the total black hole mass is around 4×10 to the 6, so it's only like, it's about, it's not quite 10%, but it's a pretty small percentage.
So theoretically, so what you're saying then is that you could theoretically extract, you said 10 to the 5th?
It was 6.2 plus or minus 1.6 times 10 to the 5 solar masses.
Right. So 600,000 solar masses worth of energy from the black hole before it was out of gas. So you had stopped it spinning and there was no more energy to extract from the black hole. Is that right?
That's correct. And that would be with a 100% efficiency of extraction. Like you're not losing energy to anything else, or spin angular momentum to anything else.
But it's really interesting to me because when we think about the rotation of things, if I said like, how long is a day on Earth, you'd ask me, do you want a solar day or a sidereal day, right? If how long does it take for the sun to turn? And you'd be like, compared to what? And but you can get these answers, 24 hours, a month, whatever. And yet, when we're talking about the rotational speed of black holes, as you said, the one method that dimensionless, it's just like compared to what is the maximal speed that a black hole can theoretically go based on its mass according to Einstein's relativity, right? Like it's not like you can't pick a spot on the surface of the black hole and wait till that spot comes back around. Can you?
Well, the black hole then will split into something within the event horizon, and then we have a region called the ergosphere. So yeah, we're sort of looking at where the edge of the ergosphere is rotating with the speed of light. But interestingly, we can get a rotation. If we, as a distant observer, if we could put a black mark on one, a red mark maybe on one point and watch it go around once. For Sagittarius A star, for the spin rate we found, it would take a few minutes to spin once.
Right. Okay. And then compare that, like if we were looking at, say, M87's supermassive black hole,
That
how long would
takes
that
about
take?
a year. Wait a minute. Let's see. M87 is a few days.
A few
A few
days.
days. A few days.
A 6 billion solar mass black hole is turning itself within a few days.
And the if space-time were flat and we just wanted to say, well, what would be the range? What would be the size of the region that's sort of spinning around? It would be a region that was about the same as the orbit of Saturn in the solar system. So imagine Saturn going around once in a couple of days. That's how rapidly, and it's not it's not exact, of course, because it's not flat space time, and but yeah. So what you're imagining is something about the size of the radius of Saturn's orbit, spinning around once in a couple of days, and for Sag A star, it's a couple of minutes, and the radius of the orbit would be around a tenth of the distance to Mercury, the planet from the center of the sun, or about 10 times the radius of the sun.
And so when we go by that measurement of the amount of extractable energy, you found that, in fact, Sag A star is rotating faster, relatively speaking, than M87, right?
Well, that would be the time. The time it takes to go around once also depends on what we would call the, sort of the Schwarzschild radius, or the size of the black hole. So
for that, I guess what I'm saying is that dimensionless number, like as a percentage of its mass, Sag A star is punching above its weight compared to M87.
The dimensionless spin angular momentum I obtained with the Outflow method for M87 was 1, a maximally spinning black hole. Now it's 1 plus or minus 0.15, so it's got a healthy uncertainty to it. But so technically, in dimensionless quantities, it's spinning faster than Sag A star, which has a dimensionless spin of 0.9 plus or minus 0.06. But then if you want to convert that into a physical quantity, which is now an absolute quantity, it's not dimensionless anymore. When you say, how long is it going to take, for a spot to go around once in these approximations?
But M87 could spin faster, while Sag A star could not be spinning any faster. It is as fast as it can go.
M87 for dimensionless spin angular momentum of 1 is spinning as fast as it can go.
Okay.
However, there are other, the value we got is 1 plus or minus 0.15. I was reading a paper where someone actually got almost the same number we got for Sag A star, 0.90 plus or minus 0.06 for M87. So for M87, I don't think the number is, I think it's still fluid, and we don't have a precise value for M87. It's neat that different methods give similar results. So the outflow method, which depends on the properties of the outflow and the accretion disk and the black hole mass, gives a very similar number as methods that have nothing to do with the outflow at all for M87 and for many other black holes. So we've been able to make those comparisons for 6 local black holes that have masses of around 10 to the 7 solar masses, around 10 to 100 million solar masses. And there we can compare the outflow spin with one obtained with what's called the X-ray reflection method, where you're looking at the iron K alpha iron line being relativistically Doppler boosted as it zooms around the spinning black hole, and that gives a nice agreement. And we've also gotten good agreement with those two methods for a stellar mass black hole, where the uncertainties are really small, double digit uncertainties, and we're getting very nice agreement there. And then also for the another method applied to big quasars at very, very distant in the universe, there's a method called the continuum fitting method, which is giving the same numbers as the outflow method. And those methods have nothing to do with the outflow, whereas the outflow method depends on the outflow plus accretion disk properties and black hole mass. So it's very encouraging that they all agree.
And what story do you think this is telling you about how black holes behave in general in the universe? Are they all spinning pretty much as fast as they can?
Probably not. Probably not. I mean, well, stellar mass black holes, the LIGO groups are finding very low spins for coalescing black holes that are producing gravitational waves. Certainly with the outflow method, it's a lot easier to measure something that's rapidly spinning, because then you have the nice outflows produced by spin energy extraction. So it's a null result is hard to prove, I guess I would say. In other words, if you find something is spinning and you measure the spin, you can determine that with different methods and they agree, and so you think you've got something there. To measure that something is not spinning, I think is a more difficult challenge.
Right.
So
do we have any sense of the orientation of Sag A star compared to the orientation of the Milky Way itself?
Well, that's a very interesting question. And there are two different ways to look at that. One is the direction of, if you have an accretion disk or material orbiting the black hole, there's the direction which that is orbiting relative to the direction of the spin axis of the black hole. So that's one way to look at it. And then the other way to look at it is the spin axis of the black hole relative to the plane of the galaxy. Now, a galaxy like M87 doesn't have a plane because it's in a giant elliptical galaxy. It doesn't have a disk like the Milky Way. But in a galaxy like the Milky Way, you can ask those questions. Now, the outflow method is independent of any of that. So it doesn't answer any of those questions. It gives a magnitude of the spin. It doesn't tell you whether it's spinning in the same sense of material around it or in a different sense. And it doesn't give you an angle of the spin axis relative to the Milky Way's plane. Some people have methods where they try to measure those quantities. I think that for a relatively quiescent black hole like Sagittarius A star, it's easy to imagine, stars coming in on orbits that might be in the same direction as the spin of the black hole, but others coming in on orbits that might be opposite to that direction. So the spin of the black hole hasn't changed at all, but maybe the accretion disk, or what we would refer to as the accretion disk, may have changed, especially if it's gobbling up stars. So anyway, we don't have an answer for that for Sag A star. I have read some papers that say the spin axis is inclined at some funny angle. Well, that would be fine with me, because that is not a factor in the model or the what I would call, I guess, the ansatz, or the bigger theoretical picture that I have developed for the outflow method.
So let's say we're in the far, far future and we want to use the supermassive black hole at the heart of the Milky Way as a battery. We want to bank a lot of rotational energy into the black hole that we can then extract later on via the Penrose process. What is the best way for us to put more energy into the black hole?
Well, I think to spin up the black hole, what you would want to do is dump mass on that is orbiting in the same sense that the black hole is already orbiting, but it would take a mass similar to the mass that's already in the black hole, right? So if we already have, say, let's see, what do we have? 4 × 10⁶ solar masses roughly. That would be, you'd have to dump a lot of mass. You'd have to dump a lot of angular momentum, and when you put it, it's hard to put angular momentum into a black hole without having mass go in with it. So I think it would be difficult to spin up the black hole unless you have black hole coalescence. If you had another black hole come in with a similar mass, and then the orbital angular momentum of that binary black hole mass system could go into the final black hole spin. So I think it would be very difficult for a human to spin up a black hole, a supermassive black hole, or even a stellar mass black holes. I mean, the energies are really tremendous. They're on the order of the rest mass energy of the black hole.
But I guess you interpreted my question like, if you don't want to lose the star that you're throwing at the black hole. But what if I was okay with that? What if I'm okay with crashing stars into the black hole to both, I guess, increase its rest mass, but also increase its rotational energy?
Well, if you throw in one star, that would be like 1 solar mass, say, or 10 solar masses. The black hole is already at several 10⁶. So that isn't going to carry even, that's only going to increase it by, 1 in 100,000 or 1 in a million.
I'm patient.
So,
yeah.
Yes, you have to be very patient. You'd have to drizzle in about a mass equal to the mass of the black hole and have all of that angular momentum be maximal carried by each star and have it all go into the black hole itself. So I think it's going to be very, very difficult to spin up a black hole. It's going to be a lot easier to extract the spin energy and decrease the black hole spin mass energy. And so I view these supermassive black holes as a reservoir of energy that is going to be impacting the near and far field environments of the black hole and impacting this galaxy structure because of that, because of those interactions.
Well, it's fascinating work. Congratulations on the measurement. I really appreciate you taking the time to chat with me today.
Sure. It's my pleasure. My pleasure.
I hope you enjoyed this conversation with Dr. Ruth Daly. I am going to talk some more about black holes, but first I'd like to thank our patrons. Thanks to Dougie Stewart, Stephen Krasaki, David Richards, Mark Ansis, Joel Yancey, Antonio Lofilara, Dustin Cable, Vlad Chilipin, Monso, George, David Giltonet, Andrew M. Gross, Jeremy Mattern, Josh Schultz, and Jordan Young, who support us at the Master of the Universe level, and all of our other supporters on Patreon. Despite how complicated black holes are, and the math is complicated, they're surprisingly simple creatures. I mean, you can really only define a black hole by its mass, its spin, and its charge. And yet, when you think about every black hole and the vast, long history of all of the material that it consumed over enormous time periods, each of which is, planets, stars, gas, dust, asteroids, everything goes into these black holes. And yet, all of that information is apparently locked inside the black hole. And you're just left with the mass and the spin rate and the charge. And it's going to be really, really tricky to learn anything more about black holes. I mean, you can understand the environment that is around them, how they twist up space-time, how their event horizons, maybe even reach the photon ring of a black hole. And yet, beyond that event horizon, we have a really hard time learning anything about it. And we might never know. And I think sometimes we have to be okay with there being places in the universe that may be permanently accessible. We may never know what came before the universe. We may never know what's inside a black hole. We may never know so many mysteries. And yet we should try, we should search, we should try to find out, learn more, but still be okay with being uncertain and never maybe knowing the full answer. Now, I've done tons of questions and answer shows where we talk about black holes, so I'm just going to put 2 here that you can check out after this interview.